with the flow of heat, and also it deals with the energy changes accompanying all types of physical and chemical changes or processes. So any physical process or chemical process, they are always accompanied with the energy changes. Say for example, melting of ice, or melting of ice, or any other chemical change like the reaction of calcium oxide with water. So these are all physical and chemical changes which are always accompanied with an energy change. So the study of energy changes accompanying all types of physical and chemical changes or processes is called the thermodynamics, and that is the principal aim of the thermodynamics. And in the thermodynamics, we are coming across two generalizations, and these generalizations are called the first law of thermodynamics and the second law of thermodynamics. Actually, these laws, these generalizations, these definitions are actually generated by the human experiences. And actually, there is no formal proof for the observations made in thermodynamics. And also, nothing contrary has been observed so far. Nothing contrary so far recorded on the observations made in the thermodynamics. And one of the drawbacks of the thermodynamics is the results, the calculations, and the definitions, and all the procedures are applicable only for matter in bulk. So the matter in bulk is in chemistry called assemblages of molecules. Therefore, these things are applicable only for matter in bulk. It is not applicable to the atomic or molecular structures. So the very small atomic structures or molecular structures, these things are not applicable. So they are applicable only for materials in bulk. So this is the introduction for the thermodynamics. The generalization is the first law and the second law. And these laws are formulated by the human experiences. And there is no formal proof for these laws. And there is no a violating observation has also been observed for the laws and the processes explained in the thermodynamics. And when you think of the importance of the thermodynamics, the very famous laws or statements or rules are normally originated from the thermodynamic observations. Say, for example, want of law of dilute solutions, Raoult's law of vapor pressure lowering, distribution law, law of chemical equilibrium, phase rule, and laws of thermochemistry. And these are all the things originated from the thermodynamic observations. So these are all the importances of the thermodynamics. And the limitations. What are the limitations of the thermodynamics? Actually, the prediction of a feasibility or spontaneity of a process is also one of the advantages of thermodynamics. Using the thermodynamic calculations and the thermodynamic results, you can predict whether a particular process is feasible or whether the particular process can spontaneously take place. And these are all the advantages. And another advantage is the determination of the extent to which a particular process can proceed before attainment of equilibrium. So now, when I come to the limitations, when I come to the limitations, It is applicable, it is applicable only to material in bulk quantity, that is big assemblages, and it is not used for individual molecules. And another disadvantage is it speaks only about the feasibility of the process, but it is not telling us anything about the rate of the process. Whether the process is feasible or not, that is discussed by the thermodynamics, but the rate of a process, how fast the reaction can go on, or whether it is a slow process or whether it is a fast process, that rate is not discussed by the calculations and the theories of thermodynamics. And also it concerns only with the initial and the final state of a particular substance. It is not at all worried about the path by which the process is taken up. Say, for example, the combination of a hydrogen and oxygen. When you simply study the theory, it is possible to form the water. That is, the reaction is feasible, but the reaction is very slow. You can never initiate this process without the energy of activation, which is not discussed by the thermodynamics. It says that it is possible, but the very slow nature of this reaction is not discussed by the thermodynamic parameters. Now we are going to look into the very important terminologies very often used in thermodynamics. The first term is a system. So it is the any specified portion of a matter under study which is separated from the rest of the universe with a bounding surface. This is called a system. And another thing is a surrounding, that is the rest of the universe which is in a position to exchange energy and matter with the system. It is surrounding. So normally when normally when system in thermodynamics is studied, we think of the system under the surrounding. I request you to wait for some time. I'll be back. So, so the system is any specified portion of matter under study which is separated from the rest of the universe with a bounding surface. Bounding surface means which is a margin or which is a boundary which can separate the system and the surrounding. Actually, the energy exchange or matter exchange or work done, these are all taking place only on the boundaries. Surrounding is the rest of the universe which is in a position to exchange the matter and the energy with the system. It is called surrounding. So when you go to the next slide, what is an isolated system? Isolated system, there is no exchange of energy and matter. There is no energy exchange between the system and the surrounding, and there is no material exchange between the system and the surrounding. And another thing is a closed system. The closed system, there can be an energy exchange, but there cannot be a matter exchange. An open system, energy and the matter can be exchanged. So isolated system, say for example, thermoflask is an isolated system because you cannot, in a closed thermoflask, you cannot exchange matter, and also the heat energy inside the thermoflask is not easily coming out. So which can be taken as an example for an isolated system. A closed system, any container which is closed where material exchange is not possible. At the same time, the walls are made up of conducting material. So any hot substance which is contained in a closed system, the temperature can go down, the heat energy can come out, but the material cannot be exchanged. Such systems are called closed systems. Open system means any open tumbler containing a water, water can spill off or the temperature can come down. So there is energy and matter exchange between the system and the surrounding. So the system can be of three types: isolated system, closed system, and open system. But now we are going to discuss what is macroscopic properties. Macroscopic properties means they are the properties of macroscopic system. That is the system with big assemblages. So the thermodynamic fundamentally is not concerned with the atoms or molecules. It is only worried about the molecules in a bulk quantity, material in bulk quantity. So in big assemblages, what are the important properties to be considered when you do the thermodynamic calculations? They are called macroscopic properties. So say, for example, pressure, volume. There is no meaning in measuring the pressure of one single molecule. Pressure is only for an assemblage. Similarly, volume change is more significant only in assemblages. Temperature and viscosity, density, refractive index, even color. So these are all the properties of the assemblages. And these assemblages, as they are all big macroscopic system, they are called the macroscopic properties. And these macroscopic properties can be divided into two types called intensive properties and extensive properties. Intensive properties means the properties which are independent of the amount of the substance. Say, for example, temperature, pressure, density, concentration, viscosity, specific heat capacity, refractive index, and surface tension. So these are all the properties which are independent of the amount of the substance. Suppose if you are having a very big container with 100 liter of water, and the temperature of the 100 liter of water is 75 degrees centigrade. If you take one tumbler of water from that big container and measure the temperature, that will also be 75 degrees centigrade. I request the number 40 to come online. Who is number 40? So the properties, the intensive properties are independent of the amount of the substance. Say, for example, temperature, I have already told you the example. You may have a very big container having some thousands of liter of water where the temperature may be some 50 degrees centigrade. Even if you take a small quantity from that big container, that will also be 50 degrees centigrade. So the temperature is independent of the amount. Similarly, pressure. Pressure is force acting per unit area, and density, mass per volume, concentration, viscosity, specific heat capacity, refractive index, surface tension. So these are all some of the examples of our intensive properties. If you take extensive properties, they depend upon the quantity of the substance. Say mass, volume, energy. So they are all the examples of extensive property. And also system can be divided into two types. One is called homogeneous and the other one is called heterogeneous. So homogeneous system, which is uniform throughout and which contains only one phase, which is uniform throughout, only one phase. Suppose a solution containing a solvent and a solute is a two component system, but it is a system of single phase. Even though two components are present, but they are homogeneous, they are uniform throughout. Similarly, if you take a heterogeneous system, this is not uniform throughout, but it is a combination of two or more phases, but inside the phase it is uniform, but one phase and the other phase, they do not mingle with each other, therefore they become a heterogeneous system. Say, for example, oil and water mixed together. Oil and water mixed together, what will happen? The oil layer will be separated from the liquid layer, and there will be a line of demarcation between these two phases, and which is a heterogeneous system, which is not uniform throughout. But one layer is uniform within itself, and the other layer is uniform within itself. But these two layers, they have a very perfect line of deformation, which is called the boundary of the phase. So this is an example for heterogeneous system. And the next thing is state of a system. State of a system is when the macroscopic properties, we have already discussed what are macroscopic properties. So they are the properties of big assemblages of molecules and atoms, like a volume, temperature, composition, density, viscosity, surface tension, refractive index, and color. When, when you measure number of macroscopic properties, they are all with a particular value, a definite value, then that is called a state of a system. It is a state. Say, for example, water in the form of ice at 0 degrees centigrade. You can find out its mass, you can find out its temperature, you can find out its volume, you can find out its density, you can find out its refractive index, you can find out its other macroscopic properties. These properties have a definite value. So with these values, the water in solid state at 0 degrees centigrade is in a particular state. Now I am slowly rising the temperature. So what happens? The solid nature becomes liquid, temperature rises, volume changes, pressure changes, density changes, and all these macroscopic properties change. Now the system goes to a different state. So what is the ultimate idea of this? When there is a state change, there will be changes in the macroscopic properties. So the macroscopic properties changing is resulting in the change of the state of a system. There is a change in the state of a system when there is change in the macroscopic properties. Even a small change in any one of the macroscopic properties will result in the change of the system. It is not necessary that all the macroscopic properties should change. Even one macroscopic property changes, then the state of the system changes. So the state of a system is defined by the values of the macroscopic properties. There are a number of macroscopic properties. You may maintain all the macroscopic properties a constant, and one of the macroscopic properties may be changed. But even then, it is considered in the thermodynamics that the state of the system has completely changed. Suppose you are taking water, water is not changing its density drastically, and also volume is not changing drastically, and the color, all other components are remaining the same. But I am rising the temperature by 1 degree means that the temperature, as it is one of the macroscopic properties, it changes, and therefore it is stated that the state of the system has completely changed. Now, these macroscopic properties which change with the state is normally called the state variables. So the state of a system changes with the macroscopic properties, and these macroscopic properties actually which are the function of the macroscopic properties. The state is a function of a macroscopic property. Function means it is the mathematical rule by which two numbers can be related. So it is a mathematical rule. So state is a function of macroscopic properties. That is why the properties are called state variables. So the state variables. So in an initial state, look here, the initial state is written at the bottom. and the final state is written at the top. From initial state to final state, there is change in one or more state variables: pressure, temperature, volume, mass, composition. Now, sometimes the state variables may be interdependent or completely independent. Suppose if you take a cylinder containing gaseous substance and which contains a frictionless piston to move up and down to change the volume and the pressure, and that the gas is considered to be ideal in its nature, then what will happen? According to ideal gas equation, PV is equal to RT. So in the PV is equal to RT, there are three variables: pressure, volume, and temperature. But R is a constant. Therefore, what happens? If you maintain temperature constant, pressure and volume are inversely related. If you maintain pressure constant, then volume and temperature are directly related. If you maintain volume constant, then pressure and temperature are directly related. So from this, I can say, in order to define the state of a gaseous system, which is ideal in all its behavior, you need not mention all the three state variables. Mentioning any two variables is sufficient because the third variable can be found out by knowing the two variables. Therefore, volume is considered a dependent variable, whereas the temperature and the pressure are considered independent variable. So, knowing the temperature and pressure, the third variable can be found out. So this is how among the state variables, a few variables are called dependent variables and a few variables are called independent variables. So the dependent variable can be calculated by knowing the independent variables. So the mentioning all the variables are not necessary. You can simply mention the independent variables alone because the dependent variables can be calculated by other means. So if a system is containing only a single gas, it contains only one gas, there is no meaning in speaking about the composition of the system. So the composition becomes an invariant. It is not a variable in discussing the state of a system. Suppose if a system is closed, then what happens? There cannot be addition or deletion of substances from the system. Therefore, mass becomes a non-variant. So mass of the substance is not going to change, which cannot be a part of the state variable because the system is closed. So depending upon the condition of the system, depending upon the components present in the system, the state variables will change. I suppose you might have clearly understood what is the state variable. If you are not able to understand, I want to repeat this. State of a system is defined by the macroscopic properties. Macroscopic properties means the thermodynamic properties of a very big assemblages. So these properties are defining a system. Therefore, they are called state variables. Suppose a system is in an initial state and which moves on to a final state, definitely there will be a change in one or more state variables. When you define the state variables, some of the state variables are independent and some variables are dependent. It is always worth mentioning only the independent state variables, whereas the dependent state variables can be calculated by the thermodynamic methods. So, depending upon the system, if only one gas is present in a system, then the mentioning of the composition becomes meaningless. Therefore, the composition becomes a non-variant. And also, if in a closed system, there is no meaning in mentioning the mass of the system because there is not going to be addition or deletion of the substance from the system. So, depending upon depending upon the nature of the system and the depending upon the components of the system and also the depending upon the independent and the dependent variables, the state variables may be mentioned. So another important topic in discussing this is various equilibria. Actually, the thermodynamics, what we are studying now, is called equilibrium thermodynamics. So in PG classes, you will be studying another type of equilibrium called near equilibrium thermodynamics, or non-equilibrium thermodynamics, which is also called irreversible thermodynamics. But what we are studying now is called reversible thermodynamics. So thermodynamic equilibrium means the macroscopic properties which are not changing with the time. Suppose when you measure the macroscopic properties and the time, and when the time goes on, there is no change in the macroscopic properties. So, in each phase, for example, if a heterogeneous system is considered, the macroscopic properties remain the same in each phases. So, as it is not changing with the time, the system is said to be in a thermodynamic equilibrium. So, this is called equilibrium thermodynamics. And there is a non-equilibrium thermodynamics also, which is also called irreversible thermodynamics. And the first equilibrium that we discuss here is the thermal equilibrium. See, if a system is said to be in thermal equilibrium, there is no flow of heat from one part to another. That means the temperature remains the same in all parts of the system. When the temperature remains the same in all parts of the system, you can never assume the flow of heat from one part to the other. Therefore, there is no flow of heat from one part to the another. Therefore, the system is said to be in a thermal equilibrium. Mechanical equilibrium, there is no mechanical work done by one part of the system on another part of the system. That means that the pressure remains the same throughout. Suppose if there is a pressure variation, nowadays we are experiencing the cyclones, we are experiencing the storm. It is because of the variation in the pressure, which means some work is done by the movement of the gases from the part where the pressure is high to another part where the pressure is low. Therefore, some mechanical work is done. If no mechanical work is done with the time, then the system is said to be in mechanical equilibrium. There is another equilibrium called the chemical equilibrium, which is the composition of various phases remain unaltered with the time. Actually, chemical equilibrium is an apparent state of rest of two chemical processes proceeding in opposite directions with more or less the same speed. So, with this, the class just I want to disconnect, and I want all the students to reconnect immediately because the 40 minutes is over. Please disconnect and get reconnected immediately.